I'll mention this a little bit. This is an application of this, in a sense, the idea of CFT. But I won't talk about this too much because I want to tell you a little bit about this work in progress. And the last thing is going to be, in some sense, more like an advertisement. But you'll see what I mean. This section will be a little sketchy. But let me first explain the background, even though I'm sure a lot of you know all about that already. But anyway. Okay, so what's the motivation here? So I want to find something like a C theorem in 3 dimensions, some way to count the number of degrees of freedom in interacting theory, especially for conformal field theories. You sort of want something which is monotonic along RG flow. I should say, when you say count the number of degrees of freedom, you really mean the number of variables you need to describe the system per unit volume per energy scale. Otherwise, of course, it would be kind of trivial that it would be monotonic along RG flow, because of course, when you go to the infrared description, you just throw out some UV degrees of freedom, so of course they're less. That's not what one means. You really mean that the sort of the local Lagrangian looks like it has less fields in the infrared than the UV, say, if they were both described by free fields. But how are you supposed to generalize that to some interacting theories? And I'm going to really only talk about this in the context of supersymmetric theories, so I'll tell you how to put them on round spheres, which you probably know, but I'll review that, how they localize, and then I'll talk about these holographic examples. So the first one comes if you put n M5 branes on a Calabi-Yau fourfold column, then you get some dual like ADS4 times the Sasaki-Einstein, and you can match this field theory calculation of this sphere free energy with the gravity calculation. And then I'll also talk to you about this new stuff, which is putting n M5 branes on a 3 manifold. And there we don't have an explicit field theory dual, but through some kind of trick, we can still compare something on gravity and field theory sides. So, okay, so I sort of said this already. Of course, the most obvious thing you could think of that would be a kind of measure of the degrees of freedom, was probably what people first meant, was the thermal free energy. So you just heat the thing up to high temperatures, and the leading term looks like the volume times the temperature to the power of the spatial dimension. So it's dimensionless with some coefficient, and that's the coefficient you think you're talking about. But that thing isn't actually monotonic, and it's, for instance, it's not constant along conformal manifolds. So if I have some CFT and I move along exactly marginal directions, the thermal free energy just changes. And in 3 dimensions, you can find lots of counterexamples, really in any dimension. It only works in 1 + 1 dimensions. So in 1 + 1 dimensions, the thermal free energy is the same as the Zamolodchikov C, and so it is monotonic, but otherwise not. Okay, but in some ways, it's more natural, even in 2 dimensions, to think of the quantity as being the coefficient of the trace anomalies. So you, in a conformal field theory, you think that the trace of the stress tensor is just 0, and indeed, on the right-hand side, no non-trivial operators set, but there's some kind of anomaly, and so you get some expressions that just involve the background field. So in flat space, in flat space it's just 0, and in curved space you pick up some contributions like this. So if 2 dimensions, you just have the Euler density. So it's this coefficient which is monotonic, and the RG flow actually looks like gradient flow. So that's from a long time ago. And in 4 dimensions, annoyingly, the name C is switched with A, but it's still the same coefficient of the Euler density, which is supposed to be monotonic. And actually, there's, I forgot to write here, there's seemingly proof of this now by Komagodsky and Schwimmer. And again, it's some kind of anomaly coefficient. So of course, you could show by sort of anomaly matching that it's constant on conformal manifolds, and sort of using similar logic, they proved the monotonicity. Yeah, it's an interesting paper. But in odd dimensions, there aren't any anomalies, so it's not clear what you're supposed to do. Can't be something like this. These guys have, I should say, the nice feature that it's some kind of local, it's sort of locally defined. So it appears as a coefficient of some local term and the effective action of background fields. So you take your CFT and you couple it to, say, a metric in the dilaton, and you try to write down the effective action for the metric, background metric and dilaton, and you'll find some particular terms which are local because it's an anomaly, because it comes from a logarithmic divergence. So you can try to pick out these coefficients. Well, before I continue with that part of the story, let me just mention something else. So just remind you of something. So in these 3D theories that I'm going to mostly talk about with n equals 2 supersymmetry, they have 4 supercharges, and so they can admit U1R symmetries. And of course, if I ever have a U1R symmetry and I combine it with an abelian flavor symmetry, it's still an R symmetry, just because it still satisfies the same commutation relations with the supercharges. But at the fixed points of the RG flow, so that the conformal field theories, they have to have the R symmetry. In general, you could have it or not, might be broken by, say, superpotential or something. And now it appears in the right-hand side of the algebra, if you like. It appears in anti-commutators of the supercharges with the superconformal charges. So there's a unique charge that sits in the superconformal algebra. Of course, so now I can't shift it by flavor charges. If I did, it would still be an R symmetry, but it wouldn't be this superconformal one. And it's nice to know what this thing is because it determines, for instance, the dimension of all chiral primaries, so they're just equal to their R charge. And but in these theories with only 4 supercharges, the R symmetry is abelian, and somehow it's a non-trivial problem to determine which actually is the charge that sits in that algebra. So in particular, if you started in the UV, say with something involving free fields, which have canonical R-charge assignments, by the time you flow through the infrared, the thing that sits in the infrared superconformal algebra might have been mixed with some flavor symmetries like this. So this game of trying to determine the infrared R symmetry means finding these coefficients between the R infrared and R UV, the relative difference by the flavor charges. Okay, of course, I should say in the examples I'm going to talk about, the infrared R charge and the UV R charge differ by flavor symmetries that you see already in the UV theory. In general, it doesn't have to be. You might mix with accidental symmetries, and then it's much harder to find what the infrared R charge is. That actually happens with the n equals 8 super Yang melts, which maybe I'll mention in a little while. Okay, so in 4 dimensions, this whole problem was solved a while ago in a nice way. So basically, all those terms are some anomaly coefficients, and so there are nice non-renormalization theorems for them. And it turns out that you can, if you knew the superconformal R symmetry, you could simply compute the trace anomaly through this kind of simple formula. It looks kind of a funny formula because so this is supposed to be, this trace is like a sum over all of the fermions in the theory, like just over the fields that appear in the Lagrangian. So it looks kind of like a UV formula, and then you plug in the infrared superconformal R charge to compute the infrared A, but it's because of this matching of anomalies. There's a non-renormalization. And then in Trilligator and Weck showed that actually if you take this function and put in some guess for what this R is, that is, by the mixing with flavor symmetries, then it's maximized as a function of that guess. So not only does it compute for you A in terms of R, it also computes R and therefore A. And so if you specify a Lagrangian of an n equals 1 theory in 4 dimensions, which flows to some CFT, as long as there are no accidental flavor symmetries, you can get all of these quantities in some nice way. And moreover, it gives you evidence for the A theorem. Maybe that's moot now because there's a general non-supersymmetric proof. But the logic here was that because you were supposed to maximize A over the mixings of the R symmetry with flavor symmetries, usually in an RG flow, you add some term to the superpotential, some relevant operator will break flavor symmetries. You know, if I had trace phi squared, I won't have the symmetry that rotates the phase of phi anymore, something like that. But everything else will be the same. The superpotential terms don't explicitly enter here. It just says that I tried to maximize it over a smaller space, so the value will be less. And of course, the hole in that is there might be accidental symmetries, but now it looks like a general proof. It doesn't have anything to do with supersymmetry, this Komargarsky-Schwimmer proof. So now back to 3 dimensions. So something that had been proposed to determine the R charge, the superconformal R charge in 3 dimensions, was that if you look at the numerical coefficient in the first term of the 2-point function of an R current with another R current, whether they're the superconformal ones or not, it turns out that it's maximized if you put there the superconformal one. So you look at the 2-point function of this R current with itself, and you look at the value of it, that they call tau, and it's maximized to the superconformal R current. And this was proven because to do with the multiplet structure of the currents. But the quantity that sits there doesn't look like it's something easy to calculate. So it receives quantum corrections, and one doesn't know how to calculate it. It's also known to not be monotonic, so it doesn't seem to do the job, even though it's a true statement, but doesn't answer the question. And then something which at first sounds something completely different. So I'm going to say that the answer is the SC partition function, but something which sounded completely different was this entanglement entropy. So the idea there is you have, say, a d-dimensional field theory. So you think of it in d-1 spatial dimensions times time. I just cut out a ball, a round ball in the d-1 space. So ball of radius r. So in this case, I just draw a circle. So it's 2 plus 1, so I just draw a circle in the plane. And you compute the entanglement entropy. So it means like you imagine you're restricted to live in this circle. You just take the vacuum state, but you trace over the Hilbert space outside. And so now the vacuum in this restricted region looks like some density matrix, and you compute the entropy. That's this entanglement entropy. Oops. This works. Interesting. Very nice. So, right. So that's called the entanglement entropy. In a sense, I think you can think about it as if you're an observer that sits in Minkowski space, and you look back in time for some amount of time t, and you just see the vacuum looks like a non-trivial density matrix to you at time, t in the past, because you can't see outside of the light cone, so you exactly look at this density matrix. Of course, that doesn't prove in any obvious way that it's monotonic, because it's not a closed system. So, of course, the entropy is supposed to increase by the second law, but stuff goes outside the light cone. So it seems perhaps hard to prove, but these guys, Myers and Sinha, had some holographic evidence at first that this entanglement entropy was monotonic and agreed with A in 4 dimensions and C in 2 dimensions. And then later they argued that it was really equivalent in 3 dimensions to this sphere partition function for conformal field theories. So for non-conformal field theories, there's no relation between the partition function on the sphere. In general, you wouldn't even know how to define it. Right, how do you put a non-conformal field theory on the sphere? You have to tell me there's some choices. And this entanglement entropy, which you can just define for any field theory. And right, so they showed it was equivalent, but there still seems to be perhaps in this argument some subtleties to do with divergences. And yeah, so I don't know if it's a complete proof or not. On the other hand, in this world of entanglement entropies, Cassini and Huerta recently showed that if you make this combination, so I should say the entanglement entropy has some trivial kind of UV divergence near the boundary of the circle, or the ball. So there's some divergent piece which is just proportional to in the 2 plus 1 case, the circumference of the circle. So that you want to throw away, so that's what this subtraction is designed to do. So you throw out this divergent piece, so it has some linear divergence in R, so you throw that out, and then they actually show that this whole quantity is just monotonic. So in any field theory with any, like if I choose any regulator in any field theory, this thing is going to be monotonic. So then if you also believe this statement, it proves the F theorem. But there's some kind of, perhaps some small subtleties in the relation to the sphere partition function exactly related to some kind of divergent terms, so it's not totally clear. But part of the trouble is that in the entanglement entropy, so in the entanglement entropy, it's, I'll explain it in a few slides, I think, it'll be clear. I'll come back to that. Well, why it's a little subtle. The question is whether this entanglement entropy is intrinsically defined, or the value gets shifted if you change the cutoff prescription. So this monotonicity is independent of that statement, but the relation to the superpartition function, of course, depends on it. So I'll come back to it.
Daniel?
Yeah.
In 4 dimensions, does the entanglement entropy have to do with the partition function on the 4th sphere or not?
Well, yes, but of course, in 4 dimensions, the partition function on the 4th sphere has the logarithmic divergence. So the only thing that's meaningful is the coefficient of the logarithm, which is a, and indeed the entanglement entropy is related to a. So it's supposed to be, I think, sort of uniform in all dimensions.
But there is a difference between odd and even for that.
Yeah, that's right. I mean, the difference is that, of course, like when I say it's the same, like, for instance, the entanglement entropy is not actually the, well, it's going to be sort of the coefficient of the logarithmically divergent term in the entanglement entropy, which the entanglement entropy is always really related to the superpartition function. So it also has the same difference between even and odd dimensions. Yeah. Okay, so what about, but of course this entanglement entropy is extremely hard to calculate, whereas this superpartition function is much easier, and in supersymmetric theories you can do it exactly. So this game for S3, it kind of generalizes some work of Princeton on localization on S4 for 4D gauge theories. But on S3 it was started by Kapustin, Willett, and Yakov, and their calculation worked when you didn't have any anomalous dimensions. In other words, when you never mix the flavor symmetries with the R symmetry, like I mentioned. So it basically meant that worked for theories with n equals 3 or more supersymmetry. And then you have a non-abelian R symmetry and you can't mix it. Okay, and then on the other hand, there's some relation of this quantity to, I mean, one reason why it's natural to think that it measures something like the number of degrees of freedom is that in theories with holographic duals, what's the S3 partition function? Well, it's the log of it is given in the classical supergravity approximation by minus the Euclidean action in ADS. So just this guy, and it basically just measures 1 over the 4D G nu n. So in other words, it just tells you the sort of size of the ADS in 4D Planck units, which is some measure of the number of degrees of freedom per unit volume per unit energy. Per unit energy, because the ADS sort of automatically geometrizes the scale direction. Okay, so using this exact calculation, one ends up with some kind of matrix integral. So if you have a large N gauge theory, you can try to solve it using large N techniques. And this was first done for the N equals 6 theory, describing this NM2 branes in C4 mod ZK by Drucker, Mourinho, and Putrov, and they found indeed that n to the 3 halves behavior that, you know, one. So that's the first time one could see that from field theory. I should mention here that one thing which is kind of funny is you might have thought after all of this, you could have just taken the n equals 8 super Yang-Mills, put it on S3, and used the same kind of localization procedure and also calculated n to the 3 halves. And the reason why it doesn't work is because in the n equals 8 Yang-Mills, you have an SO7R symmetry, which gets enhanced to SO8, and that doesn't sound like by a lot, except that the super conformal R charge definitely lives in the part of the SO8 you don't have. That's sort of obvious because even in the single M5 brane case, you know that you're going to have to dualize the photon to get one of the 8 scalars, and that guy is supposed to have the same dimension as the other ones, but there's no way that it can have a non-trivial R charge from the point of view of the n equals 8 Yang-Mills. So you can never get the right guy. And in fact, if you just blindly apply these techniques to the n equals 8 theory, you get some divergent integral, so it doesn't even make sense. This is a nice paper of Kapustin and collaborators where they add to the n equals 8 theory a single hypermultiplet, breaks it to n equals 4. So it has n equals 4 vector, n equals 4 hypermultiplet adjoint, and a hypermultiplet fundamental. That's like the theory of ND2 branes with 1D6. And so in the infrared, it's like NM2 branes and a Taub knot, and it just looks like the theory in flat space. And there they actually showed analytically that the integral is the same as this n equals 6 integral. So from that theory, you could have found n to the 3 halves already without writing down the infrared Lagrangian. but not from the
That's
n equals a.
the billion cases.
No, not a billion. Yeah, I think they proved that the matrix integrals are just identical as analytically for any n. I mean, for finite n and I mean, yeah, it's kind of funny. Some kind of, I don't know, it's some weird integral identities. Yeah, I should have. I can look up the reference later. So anyway, so why is this S3 partition function even well defined? Like usually, you think that you're supposed to talk about, you know, vivs of operators or kind of normalize things by the partition function. But here I want to actually talk about the number. Okay, this is kind of an obvious point, but maybe it deserves repeating. So, of course, in general, if I had some effective field theory with a lower cutoff, I'll calculate all of the same answers, except that I may have to include some local effective action for background fields. So if I have some field theory coupled to a bunch of background fields, and I try to work in a low energy theory with a lower cutoff, I'm going to induce some terms for the background fields, and that are part of the RG flow, that so the things that I integrated out. And in particular here, I'm just putting things on spheres. So if I forget about supersymmetry for a minute, I'm just taking my CFT and putting it on a sphere. So the only thing I turn on are these gravitational backgrounds, and what are the local actioning right, things like this and that. And of course, in any even dimension, I always have the Euler density, which just integrates to a number, say on the sphere or on any manifold. And so that means, because that means that if I compute in even dimensions, let's say, the partition function with some cutoff, and I use the different cutoff, it will differ in general by something like this, where E is the Euler number of the manifold. So I get some kind of ratio of the two cutoff scales to some power, which is coming from this constant, and also this number, which for the sphere, say, is non-zero, and in fact, it just calculates this thing A. So this is the fact that in even dimensions, you get logarithmic divergences. But in odd dimensions, of course, you can't have it. It's obvious that there's no quantity, well, there's no parity invariant quantity which integrates to a number in odd dimensions, because you need an odd number of, I mean, because the dimension of the space is odd. But, so all of the terms just depend on the radius of the sphere. None of them integrate to a pure number, so they look like the power law divergences of the field theory. And if you're talking about a conformal field theory, you can just throw them out, because they violate Weyl invariance. You can distinguish. So for odd dimensional theories, this partition function is just well defined. It's just a number. I mean, one way to think about it is, you know, suppose you're worried about the path integral measure. How do you know I don't multiply it by 5? But if I do it in a consistent way, I have to multiply all the infinitely many integrals by 5, let's say. But because I have an odd number of spatial dimensions, I'm always going to get 5 to the power r cubed when I do that, right? 5 to the power of the volume of the space. So I can distinguish it from a pure number. It breaks Weyl invariance. Okay, so I should say that there is something which integrates in 3 dimensions to a number, like the gravitational Chen-Simons stem. This is the, yeah. But of course, by parity or reflection positivity in Euclidean signature, it only affects the phase. So you might say that the phase isn't well defined. But of course, usually you think about regulators which don't break reflection positivity, which is the Euclidean version of unitarity. And so of course, if you talk about those kind of regulators, you never generate the phase, because the partition function is always a real number for unitary theories on the sphere. But actually in the supersymmetric calculation, you do get some non-trivial phase. So I'll come back to that. Okay, so the idea is going to be that you consider the theory on S3. Actually, that was kind of Cardy's original motivation in 4 dimensions for talking about A as the number of degrees of freedom. So it seems like that's a good thing to do. And after you remove those power law divergences, the thing is finite. Oh, I should have forgot to say here. In this story, the reason why the S3 partition function is just a number that doesn't intrinsically defined number for conformal field theory, it's exactly this kind of argument that we don't seem to have for the entanglement entropy directly. Because the crucial thing here is that when you change the cutoff, the answer can only differ by some local action for the background fields. But if you talk about something like entanglement entropy, what do you mean by local action? Right? You could write down some kind of effective action for the boundary, like if you imagine you actually put physical walls there to make the entanglement entropy, but it's not quite clear what the rules are, whether you really generate local things or not. The other thing I want to mention again is that this odd dimensional sphere partition function, because it doesn't have the logarithmic divergence and it's just a number, is not really a local quantity in the field theory. So it's not like I can write down some effective action for background fields and pick out this SC partition function as a coefficient sitting somewhere in some local term. It doesn't work like that. And I think you can see it actually can't work like that because from the answer you can see very non-trivial dependence on things like Chern-Simons terms, which like even the pure Chern-Simons theory has a non-trivial answer for this sphere partition function. And you could never get such a thing from some local term because it has no local degrees of freedom. It wouldn't make sense. So somehow the thing which is monotonic in odd dimensions has to be kind of non-local quantity in some sense. Okay, so in the supersymmetric story, one is going to try to take the supersymmetric theory and put it on S3, and it turns out you can do that presuming supersymmetry, whether it's conformal or not, as long as it has an R symmetry. But when you do it, the action you write down sort of depends on a particular choice of R charge. And so then you can calculate the answer exactly using localization, but it's a function of that choice. And it will turn out, so if you plug in the infrared superconformal one, you'll get the infrared answer for the SC partition function, just like in the case of A in 4 dimensions. And moreover, it's also actually minimized by the infrared one, so it also determines that guy. So it's very analogous to 4 dimensions, just the expressions are a lot more complicated. It's not going to be a cubic function. So just to remind you of something really basic, I mostly have in mind these N=2 Chern-Simons matter theories. So I have, instead of Yang-Mills terms, which are irrelevant operators, if you like, in 3 dimensions, like they don't do anything in the infrared, they just make the theory free in the UV. You think of them as kind of regulators, super normalizable. But more interesting are these Chern-Simons actions with quantized couplings. Once I couple them to matter, they're no longer topological, but they give you interesting CFTs. And I mean, if you write out the full action and components, you get some guy like this, which is classically conformal invariant. And if I don't have any superpotential, it's also quantum mechanically conformally invariant, up to maybe some renormalization of the Chern-Simons level. So I get lots of CFTs this way. And for that kind of theory, the recipe for the answer is some matrix model like this. So you get an integral over the Cartan of the gauge group. And so, so this is going to come from some kind of supersymmetric localization. The only BPS configurations are just ones where all the fields are set to 0 on the sphere, except for the scalar that sits in the vector multiply. That's these sigmas. And so you just integrate over the constant vebs for them. And when you're supposed to evaluate the action on those BPS configurations, and the whole thing just evaluates to 0 except the Chern-Simons terms, which give you this quadratic piece. This is really k times the trace. And then you have some kind of one-loop determinants. So you get one guy from the vector multiplets, and this more complicated thing from the chiral multiplets, the charged chiral multiplets. And here, these deltas are exactly the R charges that's associated to the R symmetry that you chose when you put the theory on the sphere. So at this point, it's some undetermined parameter, and for any value the thing makes sense. It's the partition function of the theorem put on the sphere in a certain way. But if you want to talk about the infrared theory, you're supposed to pick the right values here. So that's the story. Okay, and you get this kind of funny function when you compute the one-loop determinants for the matter fields. You're just integrating the sort of angular momentum modes on the sphere, if you like. Okay. so what's the structure of this thing? So in 3 dimensions, the conformal group is USP4, and in Euclidean signature, you get the real form SO4 comma 1. Now on S3, you have the same group, but the interpretation is a little different. The whole SO4 acts as just rotations of the sphere, and then the only other generators are the dilations around points which get rotating around. So that's the structure of the group. And if you add to it n equals 2 supersymmetry, then you have this superconformal group OSP 2/4, which contains the U1R symmetry here. Okay, so any theory like this, any theory in flat space with n equals 2 superconformal, of course I can put on the sphere using conformal transformation because the sphere is conformally flat, but in fact it has the same superconformal group as flat space. But you can also just put theories without conformal invariance on the sphere, and this is basically because it has homogeneous killing spinors, which satisfy this equation so that the supercharge is squared to isometries rather than to conformal transformation. So it's kind of like, from the point of view of this algebra, it's like keeping Q and S and throwing away Q bar and S bar. Sounds like a weird thing to do, but in Euclidean signature, that's fine. And it's of course also closely related to the 4D superconformal index. When you take an n equals 1 theory in 4 dimensions on S3 times R, it's compactifying this, you'll get this S3 star. I should note you can also put 3D n equals 1 theories on S3, preserving supersymmetry. You just take the supergroup, I'm going to say it on the next page. So you take the supergroup OSP 1/2 times SC2, makes sense. You can't do anything with them. You can't apply localization to those n equals 1 theories for a reason I'll describe shortly. So this group, of course, doesn't contain any of the conformal generators. And so it's just like pure supersymmetry on the sphere, corresponding to the fact that I had those homogeneous killing spinors. And in the supersymmetry algebra, on the right-hand side, I still get the R charge. So that always happens with these supersymmetric theories on spheres. And of course, parity would exchange these two SC2s, and it's just broken explicitly by this algebra. So you can write down, the supersymmetry variations for the fields, and probably a nice way to think about how all this is organized is like in this paper of Festuccia and Seiberg, where they mostly talked about 4 dimensions, but it works the same in general. You take your theory and couple it to supergravity, and then you put it in any background. You put it on the sphere with whatever background you want, and then you go to the rigid limit and see if you preserved any rigid supersymmetry. And in general, if I take some background like the sphere, if I just turned on the background metric and no other background fields, I'll never preserve rigid supersymmetry. I also have to turn on some other background fields, usually like the background R gauge field. And precisely because I'm turning on the background R gauge field, I have to pick which R symmetry I want to set. That's why it sits in the algebra. And then you'll get you reproduce these kind of transformations. So that's sort of the logic. But if you like, it's a way of specifying the couplings to curvature of some non-conformal theory. And of course, if it were conformal, then you could just determine it uniquely by requiring Weil invariance. But in general, that doesn't work. Okay, but once you choose the R symmetry that's going to sit in this algebra, then this supersymmetry algebra does determine the couplings uniquely. So that's your choice, and once you make it, you get some kind of this, say, for the free chiral multiplet, you get some expression like this. This term, say, is what, if I set delta equals to half, which is the canonical value for a free field, conformal coupling for a free field, this would reproduce the conformal mass of the free boson on the sphere. Okay, so this is what one does in general. Right. Okay, and then the point of localization, in a sense, is it's like a non-renormalization theorem. It says that the partition function doesn't depend on the radius of the sphere, even for the non-conformal theories, as long as you preserve what algebra you're preserving, as long as you keep preserving the same supersymmetry algebra. So it's sort of an RG-independent quantity in that sense. And so if you take the R charge that sits in the superconformal algebra and plug it into the UV expression, you get the right answer. So the UV calculation is like the calculation on a tiny sphere, and the point is it gives you the same as the answer on a big sphere. I should say there's some kind of subtlety, small subtlety here, which is that because one didn't just turn on the background metric to preserve supersymmetry, but also some other fields, you may generate, I mean, this partition function will be the same, but there may be differences between the effective actions for the background fields between the UV and the infrared, and that leads to some effects that I'll mention later. And I think there's a paper to appear of groups at IS and Weizmann Institute that will talk about some of those issues in a lot of detail. But I can't give away exactly what they're going to say. But okay, so right, so what was the idea of localization? So probably the simplest way to say it is just that if I have some finite or some well-defined Euclidean path integral, which is supersymmetric, then let me organize the integration over the fields into include one collective coordinate which corresponds to the supersymmetry variation, so it's some Grassmann direction. Now if q squares to 0, then part of the path integral is just that Grassmann integration of a constant because it's supersymmetric, so it just gives 0. It's like integral d theta, which is 0, except at the fixed points. Well, alternatively, you can imagine that you add some localizing action which is q exact and so doesn't change the answer. And if this thing is something which is positive definite on the whole field space, you add it with a huge coefficient and it just truncates the path integral to the configurations where it's vanishing. This is why it doesn't work, say, for n equals 1, 3D n equals 1 on S3, because there the supersymmetry doesn't square to 0, it squares to something non-trivial. You might think that's also okay. If it squared to some, say, rotation, I could just do the rotation first and then apply the same argument. But in these n equals 1 theories, it squares to complexified isometry, which doesn't preserve the contour of integration in field space. So it doesn't actually make sense to do that bosonic integral first. I mean, it changes the answer. So you sort of need at least n equals 2 supersymmetry somehow. Okay, so this I won't, let me not discuss this in detail because I have other things I want to talk about, but one thing to note is that the supersymmetrization of the Yang-Mills action is just Q exact, so the answer in particular doesn't depend on Yang-Mills. And the supersymmetrization of the bosonic, of the chiral multiplet action is also Q exact, the thing I wrote before, so it also doesn't depend on the coefficient of that either. And here you see, when you supersymmetrize this guy, you actually don't generate the conformal mass for the particular combination sigma equals minus the d. D was the auxiliary field. So basically, if I just change my definition by shifting the auxiliary fields, this field sigma remains massless on the sphere. That's why it still has some zero moment to integrate over. So this guy is not conformally coupled, which might sound a little funny, but it's really because the 3D Yang-Mills is not conformally invariant. It's like some scale invariant but not conformally invariant thing. And if I tried to compute, say, just the bosonic part, the partition function of free U1 gauge field on S3, it actually has a logarithmic divergence, which you're not supposed to get in 3 dimensions, but it's because, it's the same as a scalar field. The abelian bosonic Yang-Mills is the same as a periodic real scalar. And for a periodic real scalar, you can't introduce the conformal mass because it violates the shift symmetry. But the path integral is still finite because when you do the zero mode integral, you integrate over the circles. It's fine, but it gives you some logarithm. So that's okay because it's not a CFT, so you just put it on the sphere in this funny way. And of course, this guy, yeah. Okay, let me not belabor that. And the only thing that looks non-zero on the space of supersymmetric configurations that you integrate over is the term Simon's action, which just gives you a mass for this field sigma. And of course, it has this factor of I because you're a Euclidean signature. And I think I mentioned this already, so I'll skip it. And then you compute one-loop determinants. So for the vector multiplets, you get some measure like that, which sort of like, this part is 1 over the Van de Mond measure you get from diagonalizing to the Cartan, and so it just cancels that one, and you end up with this cinch thing. And for the matter one-loop determinants, you get this infinite product, which you have to regulate in some way. And of course, if you, so sort of the nice thing to do is to regulate it using zeta functions, and you get this. If you choose some other random regulator, then when you try to take the regulator away, you would generate those kind of effective actions for background fields, things like R times lambda cubed and R times lambda. But since you're interested in CFTs, you just throw them out. So you end up with this guy, like I said. Now, the dependence on this coupling to curvature, this background value of the R gauge field, is exactly the same. Well, if I change which R charge I used, that shifting the R charge by a flavor symmetry, that difference in the action is exactly the same as the terms I would add to the action if I turned on real masses. And real masses are something in 3D n equals 2 theories that are also associated to abelian flavor symmetries. Basically, so the real mass is, if I have some chiral multiplet Q, it's just this guy. And it doesn't look supersymmetric because it has explicit theta bars. And the way to understand it is this is some component of a vector, background vector superfield. So it preserves supersymmetry if and only if that guy is a symmetry, is a flavor symmetry. And so remember that in the supersymmetry algebra, the R charge sits in the right-hand side. So if I imagine I write the R charge as whatever one I had in UV plus some mixing with flavor charges, as was well known, when you add these real masses, you also extend the supersymmetry algebra like this, and you see it's actually the same up to this factor of I. But the actions are the same, so it's kind of an obvious thing. So it's clear that everything depends homomorphically on this combination, but it's kind of a tautology because it's just the same parameter except with the factor of I. Okay, so you can use this to relate this dependence on this coupling to curvature to just the ordinary dependence on real mass deformations, say in the flat space limit. And so then the point is that conformal invariance implies that all one-point functions, except for the identity operator, are just zero, which is also true on the sphere. So if you take this Z and you plugged in, you set all the real masses to zero, and you plug in the superconformal values for the R charge, so that on the big sphere you actually hit the infrared CFT conformally coupled to curvature, instead of coupled to curvature in some funny way, then if you look at the first derivative, it's exactly computing such a one-point function, say, of the real mass, the operator that the real mass multiplies, and so you should just give zero. But the subtlety is that there might be some non-trivial actions for the background fields, like the real masses are part of background vector multiplets, and this partition function is computed using localization is complex because you actually used the UV regulator that violated reflection positivity. Most of those supersymmetric actions had I's in them that violated reflection positivity, precisely because I had to turn on some imaginary value for this background R gauge field in order to preserve supersymmetry. I mean, the fact that it breaks reflection positivity doesn't really matter. It's just some UV regulator, if you like, and it's designed so that in the infrared, it looks like a reflection positive theory. In other words, for the CFT, if you put the superconformal theory conformally on the sphere, then it is reflection positive. But if you insist on trying to preserve supersymmetry when you go away from conformal invariance, you have to put in extra factors of I. Well, that's clear why, right? Because it's for the same reason that you don't have supersymmetry in de Sitter space, because S3 is like Euclidean de Sitter space. Okay, so this subtlety is what's addressed in this work to appear that I mentioned. But roughly speaking, if I had a parity invariant theory, the real mass is something parity odd, and so its Vev just has to vanish. So, and in the parity invariant theory, the partition function you get from this procedure is real, and this works. And in a parity violating CFT, then the imaginary part of this one-point function of the real mass has to vanish. I should say, I mean, this one-point function of the real mass, it's coming sort of from contact terms, right? It's coming from the background action. Okay, because, you know, the identity operator is parity even, and that's the only guy that can give you a Vev in flat space. So you get this. So it means that, so because the real mass is related to the couplings to curvature by a factor of I, it means that the derivative with respect to these guesses for the superconformal R charge of the absolute value of Z has to be 0. And it's really only the absolute value of Z that's completely well defined. After all, the phase could be shifted by these background gravitational consignments, which we can generate here because we use non-reflection positive UV regulators. Okay, and so the absolute value is sort of the physical thing, and its derivative is 0. And if you actually wanted to prove that it was minimized, you have to say something about the two-point functions, and it's hard because of, if you like, either these effective actions for the background fields or the contact terms in the two-point function. But so I don't do that. Okay, great. So now let me tell you about two holographic sort of applications or checks of this. So the first one is if I take NM2 branes sitting on the tip of some singular Calabi-Yau cone, then Calabi-Yau fourfold, then it will be dual to ADS4 times the Sasaki-Einstein 7 manifold. And as I said before, the log of the S3 partition function is this simple expression, and you can calculate this in these geometries and get something like n to the 3/2 divided by 1 over the square root of the volume of the Sasaki-Einstein manifold. Morally, this, I mean, you can see how this dependence on the volume arises in a simple way. I'll say it later. Okay, well, hold on. Okay, so this is the gravity calculation, and creationists, can you match it in the field theory? So you end up in the large N limit with some kind of matrix model, and you want to look at the matrix model not in the 't Hooft limit, where, so if you take matrix models in the 't Hooft limit, the eigenvalues always form a density, and the clump of them, I mean, as long as the potential is sort of some fairly ordinary kind of function, then the eigenvalues always form a density, and the clump has size of order 1. It doesn't scale with n. And so then you always end up with some free energy that looks like n squared times some function of the 't Hooft coupling at leading order. In a sense, it's like the old 't Hooft argument of why, why large N gauge series in the 't Hooft limit look like string theories. So you always expect this. But on the other hand, for large N at fixed k, it's not clear what happens. And if I wrote the generic field theory, it tends to have very wild behavior, don't form a density. On the other hand, in these series that are dual to some nice backgrounds, that can't be what happens. And in fact, it ends up, from a certain point of view, being a lot simpler than this. So you still form a density, say in these Sasaki-Einstein cases, but the clump has the size of order square root n, and that means that the long-range forces have to cancel. The different terms that appear in the if you look at the forces on the eigenvalues, different terms come with different powers of n, and so they have to cancel separately. So you end up with some kind of very simple, you sort of assume some ansatz where the clump has size of square root n, and then the action for the eigenvalue density ends up looking like some local action. It doesn't involve the complicated integral interactions which come from the inter-eigenvalue terms, because those guys have to just cancel. So it's pretty easy to solve the matrix models in those limits, and it agrees beautifully with this formula. I'm not going to describe it because I want to tell you the new thing. But let me just mention that what happens to this story of the minimization of z. So say in the Sasaki-Einstein geometry, you have, right, so suppose I take my Calabi-Yau fourfold cone. I could also consider metrics on it which are not Calabi-Yau, but are just scalar. And then the horizon manifold won't be Sasaki-Einstein, but just Sasakian. And so in the Calabi-Yau metric on the cone, I have, in its scalar form, the radial direction is paired with some direction in the horizon manifold and the Sasaki-Einstein manifold. That's called the Rib vector. But if I chose the general scalar metric on the cone that wasn't Einstein, then it would still pair the radial direction with something. It will be a different isometry of now the Sasakian manifold. So if I have, say, toric Sasaki-Einsteins, means I have some U14 isometry, this Rib vector will be one of the guys in here, and it's basically associated to the R symmetry. And so you can calculate the volume of the manifold as a function of the embedding, how this Rib vector is embedded into this U1 to the fourth, and it's minimized by the Sasaki-Einstein one. And in fact, in this case, which didn't maybe a priori have to be, although it sounds reasonable, the whole function matches the one that you get from field theory. So they both depend on the same set of parameters, a mixing of the R symmetry with other flavor symmetries. So the whole function matches, which is very nice. Okay, so what about M5 branes? So I'm going to take n M5 branes and put it on a three manifold, say a hyperbolic three manifold. So the 60 theory has to be twisted if you want to preserve supersymmetry on a generic three manifold. I mean, I talked a lot about putting theories on S3 without twisting, but S3 is special, some round metric. It has conformal killing spinners. General three manifold won't. So I imagine I put my M5 branes on R21 times M3, but the normal bundle to M3 is the cotangent bundle. And then I'll preserve supersymmetry. And then there's also some R2. So this thing preserves, it's possible, easy to check, but it preserves n equals 2 supersymmetry in 3 dimensions. And in the infrared, the CFT is independent of the metric on this three manifold. And if I have sort of generic compact three manifold, which is a compact hyperbolic three manifold, there are just no flavor symmetries at all. The guys are kind of rigid. And I get some interesting CFT, and in general, I don't know what it is. If I have n M5 branes, oops. But, okay, sorry to Gauntlet's co-authors here, but so, right, so what's the dual geometry? So it looks like AS4 times some 7 manifold, where the 7 manifold is an S4 fibration over the 3 manifold. So the way you can understand how that 7 manifold arises in this picture is, so surrounding this 3 manifold in the cotangent bundle, you have an S2. That S2 is fibered over the 3 manifold non-trivially. In here, you have an S1, and then there's also some radial direction, between this and this. So those 4 coordinates give you the S4. So it sort of looks like an S2 times S1 fibered over an interval. And it's the S2 part which is fibered non-trivially over the 3 manifold. So that's roughly the structure. And then you have n units of 4-form flux wrapping this S4. So what's the free energy look like? So it's given, of course, in units, in ADS units by 1 over the 4d g Newton, which is, of course, just the volume of the 7 manifold divided by the 11-dimensional G Newton by dimensional analysis. Oops, sorry. So up to here, would be the same in the ADS4 times Sasaki-Einstein case. But there, when you change the Sasaki-Einstein manifold, you change what the local value of the four-form field strength is, because you're supposed to, so in the Sasaki-Einstein case, you're supposed to integrate star of F4 on this Sasaki-Einstein 7 manifold, and that should be equal to n. So if I change one Sasaki-Einstein for another one, its volume will be different. So in order to have the same n, I have to scale the local value of the field strength by that number. And so, of course, when I did the computation that relates this to n to the 3/2, it was the local values of the curvature that entered that calculation. So this n to the 3/2 is going to scale with the volume. So if I looked in this expression, it means that the 11-dimensional G Newton in ADS units will scale appropriately. So in that case, for instance, I would have something like n divided by the volume of the Sasaki-Einstein 7 manifold to the 3/2 coming from this part multiplied by the volume here. And you see that gives n to the 3/2 divided by the square root of the volume, which was the answer in that case. But actually in these M5 guys, it's simpler because you just wrap the M5 brane on the 3 manifold. You're always computing the integral on the S4, and the size of the S4 doesn't change when you change the 3 manifold. So it just multiplies by the volume. Just like in the case of the 4D theories you get by putting M5 branes on a Riemann surface. But here it's kind of interesting. Unlike in the Riemann surface case, if you have some compact hyperbolic 3 manifold, the volume is just determined by the topology. There's some kind of rigidity. Yeah, there are no moduli. Unlike in Riemann surfaces, you have some moduli space. These guys don't. So it's just get some number which is supposed to sit here. So how can you ever say something about this from the point of view of the field theory? So these gentlemen have some ideas of they tried to construct the field theories you get by putting 2 M2 branes on the 3 manifold. But here you want to take n in the large n limit. So I don't really know what that field theory is, but I'm going to cheat. So consider the n M5 branes on S3 times M3, and then we reduce first on the S3. So it looks like a hop vibration over S2. So if I first go down on the hop fiber to type 2a, I'll get ND4 branes on S2 times M3, and some kind of Chern-Simons term on the brane. So this is the Ramon 2 form on the S2 because this was a non-trivial vibration, and this is the Chern-Simons form on the other 2 + 1 directions, in other words on M3. So because I have this D4 theory on S2, everything just gets massive except for the gauge field. So I end up with SUN Chern-Simons on M3. And this is closely related to this SLN Chern-Simons that Demoff, Gelto, and Gukov said, so they conjectured that if I compute the squashed S3 partition function of NM5 branes on M3, it will be the same as SLN Chern-Simons on M3 at some level related to the squashing parameter. So this is sort of a different way to derive that result, if you like, but just in the special case of the round sphere. And so the duality should say that if I compute this guy in field theory, I don't know the field theory, but by field theory I mean I use this, then I'll compute the SUN Chern-Simons partition function on this 3 manifold, and in the large n limit, it should give me n cubed times the volume of the 3 manifold. And this thing looks like it's related to this 3D volume conjecture. So the volume conjecture is actually for SL2 Chern-Simons at a large value of the level, but there's some level rank duality that might connect these two things. So we're still exploring this. And then you can try to cut knots out of the 3 manifold, which introduces flavor symmetries, and then you'll have a more interesting story involving this, F maximization. And of course, then the dual geometry is a little bit more complicated. It's like the story of the M5 branes and Riemann surfaces with punctures. And once you have cut out these knots, then you can think about some kind of RG flows, and the F theorem would imply various inequalities of volumes of three manifolds. So like, you might start with the theory with some knot cut out, so it has a flavor symmetry, and then you deform by real mass, which kills the flavor symmetry, or add some, imagine you add some deformation which breaks the flavor symmetry, then the F theorem will give you some inequality on the volumes. So, okay.
Questions? Dario.
Yeah. So for this background of Gauntlet et al.,
Yes.
which is an explicit solution,
Yes, yes.
etc. So is it clear what is the matrix model that you have to write?
No. So yeah, I don't know what the field theory dual is.
These are some ideas of how to write that, but
So, right. So the idea here was to cheat. So you don't write down the field theory dual, but you use this conjecture that if you knew what it was and you computed the sphere partition function, you would get something which is equal to the Chern-Simons partition function on the three manifold. So, but that doesn't actually tell you what the field theory is, right? Necessarily.
right, but it doesn't even tell you exactly which matrix model to write. I mean, you have to reproduce exactly the same computation, the same number of this volume. That's
No. Well, the Chern-Simons partition function on the three manifold is some well-defined thing, right? One might not, I don't know how to write that in general as a matrix model, but it's something mathematically defined. Well, there are some cases where you might hope to do better, like if you can make your three manifold by taking some Riemann surface and fibering it over a circle, and when you go around the circle, you do some modular transformation, you can get fairly generic hyperbolic three manifolds in that way. So if you understood exactly how the modular transformations act on the Gauss theories of N and phi branes on the Riemann surface, then you could perhaps write down some 3D theory and find for it some large N matrix model. I should mention like the techniques of this paper look like they give very complicated. If you tried to generalize them to N and phi branes, it looks very complicated. It doesn't give you a number of eigenvalues. It scales with N. I think you get many more eigenvalues than that. So it might be even if you could actually carry out this program of cutting the three manifold into tetrahedra and using that to find the field theory, it might still be hard to solve those matrix models in the large N limit, because I don't think it will just give you n. It won't look like n times the one you get with two eigenvalues. It's something more complicated. So
yeah, so this line in the next slide over. Yeah, the top one. So you're using various conjectures there, right? You're using the AGT-like relation between
yeah. Right, so
And
this sort of uses the AGT relation and the holographic
and the 3D
relation.
volume conjecture and level rank as
Oh
well.
no. Okay, no. There are two. I think you can use either half of those or the other half of those, and they should lead to the same state. You don't need all four of them. So, in other words, if I didn't know anything about level rank duality or something, I would still make this conjecture. In other words, the logic of the conjecture is you use this AGT type relation to get this, and you use the holographic calculation to get that, and they should be equal. So you would make this conjecture, and then the attempt to check the conjecture is that you use level rank duality and the volume conjecture. But you shouldn't use all four in a sense.
No.
Well, two of them equals the other two.
That's right.
Yeah. So yes, okay.
I just have a very basic question about some background.
Yeah.
In even dimension, of course, we know there are anomalies, and then the C theorem is formulated in terms of the anomaly. In odd dimension, you have you still have the descent relation. So you still have there's a work by Fadday who proposed to interpret this candidate in the descent relation in terms of the Stringer term in the current algebra. So I don't know if any of these. I mean, you mentioned about
in terms of which on the current algebra?
the Stringer term. I mean, if you look at the current algebra, the commutator, then you usually have delta j, and then but sometimes you can also have delta pi, which is the Stringer term, which has a coefficient. In 2 dimensions, that will be the coefficient for the let's say for the Kac-Moody algebra, you have the level k in that case. Yeah.
Okay.
So I don't know if you, I mean, you mentioned something about the R current 2-point function.
Yeah.
It seems to me something like that, but I just don't know if this is actually the Stringer term or could be something like that. Has people thought about this?
Yeah, I'm not sure. Wait. So what exactly was this? The conjecture by Fadday,
I
or
don't know
what
if
was
it's
it that he
conjecture.
showed? Or
I mean, we imagine you couple your theory to some background, just like what you did for even dimension.
yes.
And in that case, you have anomaly and some anomaly polynomial stuff. And even in odd dimension, you still have something like that. That's a Stringer term.
Yeah. Okay. Sure. I see.
So maybe something.
Right. You're saying. Well, if I just had my a non-supersymmetric theory, let's say just some conformal field theory, and I look at the anomaly in even dimensions, what's the analog going to be in odd dimensions? It's saying some kind of, just like the 2-point function of the stress tensor, or what?
Yeah, I think probably the commutator of the stress tensor, and then you have the normal delta function, and then you probably have some Stringer term arising in that algebra, and maybe one can.
Yeah, I'm not sure if it's.
No, I'm not asking you to. I just don't know if.
Yeah,
what you think about this, or.
Yeah, I don't know. Yeah, sorry.
Okay, thanks, Steve.